Hi, in this video, we're going to take a look at Bayesian statistics regression. All right, so remember that Bayesian statistics is a very different approach than the classic frequentist approach to statistics. Now, we have the same goals ultimately, but how we mathematically achieve those goals are very different. In the frequentist point of view, I have no prior knowledge whatsoever. I have no information that I put from my experiences, my opinions, from literature reviews or anything like that. I take my data, data in, data out, and I get it. Well, let's say that I'm working on a project and I have years of experience on this type of project. Why can't I pull in that information to improve the ultimate result? Bayesian statistics enables this. Now, this comes with a risk, though, that by pulling in my opinions, I'm exposing my project to bias. And so we have to balance things with this. Um, you know, there's no such thing as a free lunch. We get, you know, the opportunity to improve our models with our knowledge, but we also get the opportunity to bias and throw off and degrade our models by making the choices we make. You have to make a good choice. Let's make an informed choice. And so let's talk about Bayesian regression. All right, so I'm going to take this example from Jim Albert's webpage, baseballgithub.io. And this is in the section for Bayesian computations with R. Um, all right, so let's get through this. So we're going to use prestige as our target variable. And we're going to consider the data set on prestige in Canadian occupations. And you can see that this data is pretty old, but it's good enough for our project. All right, I've got 102 rows and 6 columns. The observations are at the occupation level. And the data frames have the following information: education, the average education of the occupation people in 1971, the income, so the average income in Canadian dollars back in 1971, and then percentage of women. Okay, so this data set is coming from the car data package. And so now I'm going to go ahead and pull it in. And I'm going to go ahead and sort my data. So this is a small data problem, so I'm going to go ahead and sort things. Because sometimes by sorting, we can spot things that we wouldn't have been able to see. And so I'm going to sort by prestige, and the lesser prestige jobs will be at the top, and the greater ones will be at the bottom. And then I'm also sorting by the predictor variables that we're going to be working with. That way, maybe I could spot a correlation going on with this. Okay, so one thing that we frequently do when we're doing Bayesian statistics is that we do a baseline frequentist model. So whatever model I'm going to do in Bayesian, I do the corresponding vanilla frequentist regular statistics model as a baseline just to help me understand what's going on. The standard statistics is very, very, very well established and has a lot of tools for us to understand what's going on. And a lot of times they're just easier to interpret. So by doing this, I can, get a better feel for what's going on, and it'll help me, guide my way through my project. So I'm going to do exactly that. And so here, and this is, I'm taking this from Jim Albert's website, which was an example that, that other people came up with. Prestige is depending on education, log base 2 of income, and then percentage of women. Okay, and so we get our results here. So we've got about negative 100 of an intercept, about 4 for the slope of education, about 9 for the slope of log 2 income, and then about 0.05 for the coefficient on the percent of women. We see that percent of women is, not statistically significant, but, overall things are looking really significant. I have no qualms with this model. I got a decent R squared. All right. And it's definitely statistically significant. All right, so let's go ahead and take a look at some graphs. I'm going to go through and I'm going to color my dots red, green, and blue. So and these others are going to correspond to the lesser prestige third of the data, the middle prestige third of the data, and the upper third of prestige of the data. So red means lesser prestige, blue means greater prestige, and green is in the middle as I look at these plots. All right, so here I can go through, I can see what's going on. So, and we see that farmers and ministers and collectors for their predicted values and their observed values don't really correspond as much as we would expect. And so, you can see that definitely the FID values, there's definitely a trend going with the FID values and the colors that we see, and that's to be expected. Here's the QQ plot of the residuals, and darn, that looks normal. Pretty tight. A little bit of deviation here, but when we start getting into the sparser, like out to the left, it's not as big of a deal. There's a little bit, if there were more data points, I would be very concerned about that. Scale location, this one I don't pay that much attention to because of the other plots. Now, Cook's distance. We've got babysitters, farmers, and ministers. Okay, something interesting about that. That if we, this means that if we were to remove these, the coefficients would change more than any other data points. And then babysitters, like that's spiking up pretty high. Once again, we see farmers, ministers, and babysitters as the most extreme on the residuals versus leverage plots. The red line is pretty flat. That's looking good. All right. So now, let's actually do Bayesian regression. First thing I'm going to have to do, I'm going to have to get the data in the right format. I'm going to use the blinreg, Bayesian linear regression function in the LearnBayes package. All right, now, how it wants the data set up for this is that I need to have a 1 for the intercept, and then it's pretty standard for the X, for the predictor variable matrix or data frame. And so, so the thing that's kind of different than regular R is that I need that intercept on there, and I'm going to have the X. So it's super, super common to have X and Y format where as two separate objects in my modeling function as the inputs, but including the intercept, including a column of constant ones. You see that in a couple other places. Here it's there, it's not in the LM function. So just something to be aware of, to know of. So I have to split up. My target variable is in a vector called Y. My predictor variables are in a matrix or data frame called X, and that X needs to include the intercept. Okay, and so now let's go through. And so here's the head of the X's. Now here I'm going to simulate 50,000 draws from the posterior distribution. Okay. In Bayesian statistics, if I have the right combination of prior and likelihood, and that likelihood corresponds to my data. So if I have the right corresponding probability distribution for my prior and the right probability distribution for my actual data, I can just use a little bit of college algebra level mathematics and spit out the posterior probability distribution. That's possible in the nicest case that we can get. Unfortunately, the vast majority of cases, we can't do this. And so what we're going to end up having is that we're going to create a way to random number generation from the posterior distribution. So what I'm going to do is I'm not going to have a mathematical object like directly as in like a pencil and paper version of the resulting posterior distribution. What I'm going to have is I'm going to have a way to generate random observations from the posterior distribution. And so in an indirect manner, I'm going to get to the distribution I actually want. So the posterior distribution, remember, that comes from taking my prior distribution, the likelihood function of my data, put them together, rescale to be a probability distribution, boom, I've got a new probability distribution I call my posterior. That's the one that I actually am interested in. That's the one I want to use. If I'm in the nice case, the conjugate prior case, we're not there right now. I can just do pencil paper mathematics. I know my distribution. I know everything that's going on. Boom. 95% of the time, that's not the case. I'm gonna have to take the posterior as in an indirect manner, generate data from it rather than work with it as a pencil and paper mathematics form. So let's go ahead and do that. And so here I'm going to generate 50,000 random observations from the posterior distribution after I take my posterior with my observed data. You notice I haven't talked about the prior distribution at all. I'll talk about that in another video. Okay, so now I've got the Bayesian linear regression model fitted, and I've got 50,000 draws from it. So let's look at the posteriors. We're going to look at the marginal posterior results for the coefficients. Okay, so how Jim set this up in his example is that beta 1 is the intercept, beta 2, beta 3, and beta 4 are the predictor variables. So here, this is the posterior, marginal posterior probability distribution of the intercept. Okay, and we can see that, all right, this looks at, the mean, median, and mode is it, maybe, negative, negative 110. The order is flipped. Huh, that's interesting. Now, all right, so I've got that right here, and it's it looks pretty symmetric to my eyes. So the mean, median, mode are the same. It's unimodal. All right, so now let's go to the second one. All right, and boom, I've got that. Okay, maybe 3.7-ish on that one. Next one for beta 3, once again, looks symmetric, unimodal. So mean, median, mode are about the same. I'm going to peg that at about 9-ish for the the estimated value. And then now this is for the percentage of women in a field. I can see it's I would say just a touch less than 0.05. Okay. So let's go ahead and so these four are for the parameters of the coefficients of the model. So this is the intercept and then 3 coefficients in the model. Now let's go ahead and look at the sigma of this. So this corresponds to the variance. And we don't need this to be able to make a predicted value, but when I do my hypothesis testing, I desperately need this. And so we can see it's a slightly skew right, which isn't surprising because sigma, tends to be that way when we estimate it. And so something around 7-ish. All right, all right. All right, so now let's compute the posterior means and standard deviations of the regression coefficients. All right, so here I'm going to go through and so this is how Jim did it. I could have done column means also, that may be a little bit easier. But so here we see results that are consistent with the visualizations we just looked at. Really, this is what we're probably going to end up using as our punchline. But if I wanted to do a deeper analysis of these coefficients as a random variable, I have entire probability distribution to dig into. So I have more information than I would have had if I had a regular model. And now here I can also compute the standard deviations of each of these. All right. And let's go ahead and estimate sigma and its standard deviation. And so sigma is about 7 with a standard deviation of 0.5. So this is the standard deviation of the standard deviation. Yeah. All right, so now let's go ahead and let's say that we're interested in a particular occupation. That occupation, average education is 10 years. The average income in log $2 is 13. and the percentage of women is 20. All right, well, what are we going to get for that? So what I'm going to do, I'm going to take these values, I'm going to make this into a new row, and I'm going to, drop this into the model, and I'm going to go and do another random number generation and get an entire distribution about what the value is going to be. So first and foremost, let's try to estimate the expected value off of this. So we're going to have Bayesian linear regression expected value. So I want the expected value for an occupation with these values of the covariates. So I put the covariates in. I've got my fitted Bayesian regression model. Now here is an interesting point, because now I'm kicking off a Monte Carlo Markov chain. Notice I've got a thinning interval, number of chains, sample size, all this stuff is going on. And ultimately, I end up getting, here's the mean, here's the standard deviation of that. And here are the quantiles of it. So we can, get an idea. That's pretty tight. From 46 to 50. That's pretty tight, about 48. And now remember, this is the expected value, not the predicted value. Remember, when we do regression, expected values have more narrow intervals than prediction intervals. All right, so now suppose we are interested in predicting the prestige for a new occupation with the same set of covariates. All right, I'm going to play the same game, but I'm going to use a different function. So previously I used the function for the expected value. Now I want to use the function for the predicted value. In regular vanilla linear regression, this is similar to the difference of the interval for the expected value and the interval for the prediction. Our prediction intervals are always wider. Okay, so let's go ahead and do this. So I'm going to drop the covariate into the function with my fitted model. I'm going to use a Monte Carlo Markov chain, run through the process, and you notice I get the same mean, practically speaking, and now things are a little bit wider for me, right? My standard deviation is 7 off of that. Previously, it was 1. I mean, kind of a big difference there, all right? Was at my lower end of the quantiles was 46 now, and upper was 50, 46, 50. Now we've got 34, 62, quite a bit wider. Okay, so that shows us how to fit a model. That shows us how to get a probability distribution for the expected value for a level of observation, and to get the prediction interval like distribution. It's not an interval, it's a full-blown distribution. Now let's do model selection. So now let's say that I'm like, you know what, I've got all these models, I've got 3 predictor variables, there's 8 possible models. I'm not sure how to proceed. I don't know how to work this out. Well, you know what? The LearnBayes package is here for us, because it's going to go through the process and select the best model for us. Remember, in best model selection, I don't want to do this when I'm in a big data project or when I have a lot of covariates, because best model selection is going to go 2 to the p on the number of models it's going to consider. And so that is, p is the number of covariates. That can grow very, very quickly. And so here it's only 8 because 2 to the power 3 is 8. So it's not so bad. Like, it's not a big deal. And I only have 102 observations. Like, I'm not worried about it. But if this was a bigger data set, if I had more covariates, this would be a very bad idea. Go ahead and try it if you don't believe me, and go to sleep, get up in the morning and see that it's still computing. All right, so we're going to use Zellner's G as our prior. I'll talk about that in a later video. And here we're going to run the Bayes model selection function. It's going to compute the log F and posterior model probabilities for each model. And then the one with the largest probability is the one that I want to use. Okay, so here I'm going through, I set X and Y, And here, this parameter corresponds to Zellner's G prior. And this will correspond to a variance. The scalar adjusts the variance in the covariance matrix. Okay, and so now I'm going to sort, after I get everything out, I'm going to sort by probability and the log M. And you'll notice, so how I have this set up here, the bottom one is the one with the greatest probability, and it's by a large margin. And so I see that education is true, log 2 of income is true, women is false. That's kind of interesting. And so by this criteria, by this data, this model structure, our best model is education, log 2 income, and intercept by what we just computed. All right, I hope you have found this video useful. I hope this has helped you. Bayesian statistics is, to me, a lot of fun. I enjoy it. I don't get to use it very often at work, but I wish I did. All right, so remember, life is short. Do math.